Hello, everyone. Well, it's a pleasure to have my former student Kevin Limanta join us today to tell us about largely his PhD thesis, which was completed in 2022 at UNSW under my supervision. And the title is Super Catalan Numbers and Fourier Summations over Finite Fields. You can get it by going to the UNSW library here. So this is an important development, I think, because first of all, it explains these otherwise mysterious objects called super Catalan numbers that have intrigued combinatorialists for many decades. But it also forms a bridge between the characteristic zero story, the familiar unit circle integration that we've been talking about, and a completely discrete version over a finite field. So it turns out that in some sense, the same formulas to a certain extent apply in all these situations. And we'll see further down the road that, in fact, this algebraic approach also allows us to create a integration theory over non-compact circles, for example, relativistic circles, either in the red or the green setting, where usually physicists encounter divergence issues, things going to infinity. So it's pretty interesting. So in this initial talk, Kevin will be setting the stage for this very interesting story. I do hope you enjoy his talk.
Hello everyone, I am Kevin Limanta, a former PhD student of Norman. For a change, I will be presenting a mini lecture today, maybe also in the next one or two, about algebraic integration theory on circles. What I am presenting here is basically my PhD thesis, which I hope will be a good way to introduce to people this beautiful theory of integration and ultimately harmonic analysis presented in a more algebraic way without reference to real numbers. In the last video, Norman has pretty much captured the motivation of this mini lecture series, which is to come up with a way of defining integration over circles that work in a more general field. In this video, I will mainly talk about the setup and before we delve deeper into the subject. So we start with any field F, although in our analysis, we will exclude fields of characteristic 2, just work with either fields of characteristic P, where P is bigger than 2, or fields of characteristic 0. Okay, so for now, just say that we have a field F and consider the affine plane A, which consists of points of the form x, y, where x and y come from the field F. We consider 3 unit circles. So the idea is to work with unit circles, but we want to be more flexible and consider 3 at the same time instead of just 1. They are color coded as blue, red, and green. And this is the very idea of chromogeometry which Norman introduced. The blue unit circle is defined to be the set of points x, y in the plane where x squared plus y squared equals 1. And this 1 here is really just the multiplicative identity of the field F. So this subscript F is sometimes put to emphasize that this is coming from the field F. Okay, and this is denoted by S1 sub B. And this is pretty much the unit circle that we are most familiar with, and we can think of this as the Euclidean unit circle. The red unit circle, S1 sub R, is defined to be the collection of points x, y in A, where x squared minus y squared equals 1. So there is this subtle change of sign. Instead of plus, we have a minus sign there. Also, green unit circle, S1 sub G, is defined to be the collection of points x, y, where x, y equals 1. So the last 2 circles, the red and green circles, we can think of them as relativistic unit circles, okay, coming from relativistic geometry. And in my PhD thesis, I was mainly interested in the case where field F is finite of size, say P to the R, where P, which is the characteristic of the field, is bigger than 2. Okay. Now, the essence is this integration functional. So we want to define a linear functional I, which mimics this integration functional, and we call this I. And that takes polynomials or polynumbers of, say, in alpha and beta to the underlying field F that satisfies 3 conditions. Okay, so just we impose 3 conditions to this functional I. The first one is just a mere normalization condition, which states that, well, the polynomial or polynumber 1, which is alpha to the 0, beta to the 0, is mapped to 1 in the field. The second condition is called the locality condition. And this is really saying that if my polynomial restricts to the 0 function on the unit circle, but here I put a subscript C to indicate, well, C here is just, we can replace C by any color, blue, red, green. If P restricts to 0, function, which means pxy equals 0 for all x comma y in the unit circle, then the integral of p ought to be 0. The third condition is called invariance. Really, more specifically, we should say rotational invariance. And basically, if you have any polynomial p and any rotation matrix x, then the new polynomial that you get by doing this action, x acting on p, the integral of that is the same as the integral of p. Okay. And of course, to make sense of this, we have to define few more things, okay, to understand what, for example, what these action means, what this restriction on unit circle means. So one is to maybe carefully distinguish between polynomials with polynomial functions. Okay, so this is especially important if the field is finite. Another one is to see how the group action interacts, and this is seen in the invariance condition. And we can actually have a look at what the rotation group looks like in its geometry, the blue, red, and green geometry. Now, with this distinction between polynomials and polynomial functions, we recall again that we have this field F and we can associate to that an affine plane A, and we can think of functions from the plane A to the field F. This space of functions is denoted by this FA. And this is a vector space. If you think of the addition and scalar multiplication as being pointwise, and if we agree that we can multiply functions also pointwise, then this is really an algebra over F. Now, if I have, say, a polynomial, so a typical polynomial in this space, say is P1, which is equal to alpha cubed minus 3 alpha beta square plus half alpha to the power 4 beta. Now, what these associated polynomial function looks like is what you get if you replace alpha with x and beta with y, really. So P1 x comma y equals x cubed minus 3xy squared plus half x squared x to the power 4y. And that's really just saying, well, this is a function that takes x comma y in the plane as input, and it spits out this element in the field. x cubed minus 3x squared y squared plus half x to the power 4y. Whereas this polynumber or polynomial P1, we can think of it as a formal object. Yeah. So it is a combination, a linear combination of the monomials alpha to the k, beta to the L, say, with coefficients coming from the field F. Okay. And you can do the same with maybe this second polynomial, P2 beta minus 2 alpha square plus 3 alpha beta. The associated polynomial function is P2 x comma y equals y minus 2x squared plus 3xy. Now, this distinction is especially important if you're dealing with fields that's finite. Okay. So for example, if you have fields of size 7, then say I have this polynomial P, alpha to the 7 beta square minus alpha beta square. This is a non-zero polynomial because for some polynomial to be 0, all the coefficients must be 0. Okay. But if you look at what the associated function, polynomial function is, well, it's this pxy equals x to the 7 y square minus xy square, which we can write as x to the 7 minus x times y square. But because we're in this field with 7 elements, and this is due to Fermat, x to the 7 minus x is always 0 for any x in the field. And so essentially what we have here is a zero function because it takes any input x comma y and it gives 0 as the value. Okay, it is 0 everywhere. So we start with a non-zero polynomial, but the associated polynomial function is 0. So this might not be, very, not very apparent if you are dealing with fields of characteristic 0, because you basically just replace these alpha with x, beta with y, and pretty much you get, we don't actually need to distinguish carefully. But with this setup, if you are dealing with finite fields, for example, we do have to be mindful, of this distinction. So it pays to be more formal and maybe be more careful here in our analysis. So what we do here is we introduce a map. Okay, this conversion from polynomials to polynomial functions is captured by this evaluation map epsilon. Now, let's have a look at various group actions. We start with maybe group G, GL2F, which is just the group of 2 by 2 invertible matrices with entries in F, field F. And what we have here is, for example, if I have a matrix G that looks like A, B, C, D, we can define various actions. Then the first one is probably the most natural one. We can define a right action of G on the plane A. So if I have a point x comma y here and I have a matrix G, then G right x on A this way. So x comma y dot G is just this new point ax plus cy, bx plus dy. You can think of this as really just multiplication. This you can think of x comma y as a row vector and G as a matrix. So this is what you get really if you do that multiplication. Now with this right action of G on the plane, we can define a new action. Okay. Now this is now a left action of G on Fa, the function space, which basically takes a function f in Fa and it gives you a new function G dot f. and this function g dot f takes x comma y as the input, and it spits out f of x comma y dot g. Okay, so the role of g here is this g moves inside the bracket basically. Okay, so what it does is x comma y is mapped to f of ax plus cy bx plus dy. So we replace the x with ax plus cy, replace the y with bx plus dy. We can also define similarly a left action of g on this polynomial space. Same as before, we have a polynomial or polynumber p. Then g dot p is the new polynomial or polynumber. Basically, you replace the alpha with a alpha plus c beta and b alpha plus d beta. So for example, if I have my matrix G to be 1, 1, 0, minus 1, and say a polynomial P that looks like alpha square beta plus 2 alpha beta square, then G dot P is this new polynomial, which we get by replacing the beta with alpha minus beta. And then we fix alpha. And the reason of this is because, well, the first column of G is 1, 0. So we don't change alpha, but we do change beta to alpha minus beta because of the second column being 1 minus 1. So this is really just, alpha squared times alpha minus beta plus 2 alpha times alpha plus minus beta square, and you get this new polynomial. Now, let's have a look. If I consider, instead of p, epsilon p, which is the associated polynomial function of p, then we can check that this basically just simplifies to x squared times x minus y plus 2x times x minus y squared. And this can be checked to be, well, just the evaluation of this polynomial g dot p. Okay, so in general, it works pretty much the same. If I have a polynomial p and a matrix G, then epsilon G dot P. So the evaluation of G dot P is really just the matrix G acting on the left to this function epsilon P. Now, let's have a look at what the rotation groups look like in the blue, red, and green geometry. And this is pretty much explained pretty extensively by Norman in his Wild Linear Algebra series, and I encourage you to refer to that playlist for more detailed explanations. But in summary, what we have here is like the setup here is this so-called dihedron algebra D over F. So this dF, which is really just the algebra of 2 by 2 matrices over F. Now, as an algebra, like especially as a vector space, it has a basis, and we can choose one basis, one pleasant basis to be a basis consisting of these 4 matrices, which we call 1, I, J, and K. Okay, so 1 here, one subscript D, is really just the identity matrix 1, 0, 0, 1. Okay, here I put 1 subscript F just to, again, emphasize that this one is coming from the field F. And then there is this matrix I, which is really just 0, 1 minus 1, 0. Matrix J, which is 0, 1, 1, 0. And matrix K is 1, 0, 0, minus 1. Now, together with this algebra, we can define a map called the adjugate map. So there is this adjugation map that takes a matrix A, B, C, D, and it basically gives you a new matrix D minus B minus C and A. Okay. So we can check that if I have a matrix H in this dihedron algebra D, H times H star and 8 star times 8, they are equal, and really it's just a multiple of the identity matrix, and the scalar in front is really just the determinant of the matrix H. Okay. And if you adjugate a matrix and adjugate it again, you will end up with the same matrix you started with. And if you multiply two matrices, H1, H2, and then take the adjugate, it's just the same as doing the adjugation first, and then multiply them. But doing so, you have to reverse the order. Okay, so H1, H2 star is H2 star, H1 star. This is true for all H1, H2 in D. So together with this education map, D is really a star algebra over F. Now, there are three special subalgebras of interest here, and these are called the blue, red, and green complex numbers. And you might guess that there is this connection with the blue, red, and green unit circles that we defined at the very beginning, but we'll explain that shortly. What you can see here is the blue complex number C sub B is really just this span of 1 and I. Okay, so it's a two-dimensional subalgebra, and in its case, so if you look at this C sub R, C sub G, the matrix 1 here is always present. What differentiates between them is this I, J, and K. Okay, so red complex numbers, C sub R, this is the span of 1 and J. Green complex numbers, this is span of 1 and K. So more than that, we can check that the matrices commute, okay, with each other in its subalgebra, and that makes C sub B, C sub R, C sub G commutative star subalgebra of D. Now, with this framework, you can see that complex numbers now look like matrices, okay, because 1 and I, J, and K, they are all matrices. And this adjugation map really works as conjugation in the traditional sense. So if, for example, if I have a complex number set that looks like x times 1 plus y times I, a typical complex number, say in C sub B, then z star, which is x times 1 plus y times I star, is really just x times 1 star plus y times I star, and it is not so hard to check that 1 star is 1, but I star is negative I. So at the end, z star is just x times 1 minus y times I. So this idea of conjugation is captured here in the level of matrices as adjugation. We can define a symmetric bilinear form on this algebra D as h1 dot h2 equals half trace of h1 star h2. Okay, so again, this defines a symmetric bilinear form, and we can also, with this bilinear form, compute the associated quadratic form. So if I have a matrix H and find H dot H, I get this what I call the quadrants of H equals the determinant of H. So it's not very hard to check. And with this framework, we can define the unit circles from the perspective of matrices having quadrants 1. So the blue unit circle now can be defined as the collection of all blue complex numbers set such that the quadrants of Z equals 1. Similarly, for the red unit circle, defined as the collection of red complex numbers set such that the quadrants of Z equals 1, and same for green unit circle. Now, what you can see here, and this might not be seen very easily if you look at the definition at the very beginning in terms of points in the plane, but here you can maybe more appreciate this algebraic structure more because, for example, this is actually a group, and this can be actually seen from the fact that, well, the quadrants is multiplicative because it's nothing but the determinant. So for example, if I have two matrices or two elements in, say, blue complex number, H1, H2, since Q of H1, H2, the quadrants is really just the determinant. We have the determinant of H1, H2, which is multiplicative. So we have determinant of H1 times determinant of H2, really is just Q of H1 times Q of H2. Now, how do we connect this with the unit circles that we see at the beginning? Well, we can associate this, for example, blue complex number and red complex number, x times 1 plus yi and x times 1 plus yj, with just the point x comma y, the plane. The association for the green complex number is slightly different. Here we associate the complex number x times 1 plus y times k, not with x comma y, but with x plus y comma x minus y. Okay, you can check that this association is actually a bijection, and we do get the definition of these unit circles at the beginning if you look from this point of view. Now, the rotation group SO, well, sub C now to F is really just the subgroup of GL2 that preserves the bilinear form that we defined previously. Now, this is restricted to the subalgebra C of color C of determinant 1. And this is really just the unit circle S1. Okay, so for example, the blue rotation group SO sub B, viewed this way, is really just the set of matrices of the form x, y minus y, x. So this is really just x times 1 plus y times I, this matrix here, where the determinant of that is 1, which is just x squared plus y squared equals 1. Okay, now this equation, well, there is this very well-known rational parameterization. So think of, well, what the people will usually call it cosine, like trigonometric parameterization, like a cosine sine. But now, because we want to avoid reference to real numbers and work with a more general sort of framework that works in any field without recourse to infinite processes, we want to avoid that completely. Okay, so we want to steer away from this mention of sine and cosine and purely work, in the field, generally without any mention of infinite processes. And this is actually possible. So say here, this equation x squared plus y squared equals 1, well, this can be parameterized. So every point that satisfies x squared plus y squared equals 1, except for one single point, minus 1, 0, can be written as 1 minus t squared plus 1 plus t squared for the x component and 2t over 1 plus t squared for the y component, for where t is in the field. So this way, we can rewrite this as just the collection of all matrices of the form 1 over 1 plus t squared times this 1 minus t squared, 2t minus 2t, 1 minus t squared, where t is in the field where 1 plus t squared is non-zero. And this is important because, for example, fields might be finite and 1 plus t squared might actually be 0. Over rationals, 1 plus t squared is never 0. So it is fine. Okay, so 1 plus t squared, we are not dividing by 0. But sometimes you do get situations where 1 plus t squared equals 0. If you're allowing yourself to work with more general fields. And because of well, minus 1 comma 0, the point minus 1 comma 0 is not able to be written this way, we have to add this matrix that corresponds to x equals minus 1, y equals 0. So this matrix is just this minus 1. So when x equals minus 1 and y equals 0, you do get minus 1, 0, 0, minus 1, which is minus the identity matrix. The same can be said about the red rotation group, SO sub R. So this is the set of all matrices of the form x, y, yx of determinant 1. That basically simplifies to x squared minus y squared equals 1. Similar to the blue case, we can parameterize this. Every point that satisfies this equation, x squared minus y squared equals 1, except for 1 point minus 1 comma 0 can be written as x equals 1 plus t squared over 1 minus t squared, y equals 2t over 1 minus t squared. Therefore, we can write SO sub R this way, where we have to add, again, this special matrix minus 1 that comes from this point x comma y equals minus 1 comma 0. This time, the restriction is that 1 minus t squared is non-zero, and in any field, we get at least t equals 1, and if your field is not of characteristic 2, you also get minus 1. So if we are working with in fields of characteristic not equal to 2, we do get 1 and minus 1 to exclude from. And maybe the easiest one is actually the green rotation group, because this is just the collection of matrices of the form x0, 0, y, where xy equals 1. And this defining equation is very easy to tackle, because if I let x equals t, then y is equal to, well, 1 over t. So as long as your t is non-zero, then I can write this way. So t 0, 0, 1 over t, where t is coming from the field f, where t is non-zero. I might also mention that, well, especially, well, the size of these rotation groups, and essentially the size of the unit circles, depend on the characteristic of the field, especially if your field is finite. So there is actually, this set here is actually finite set. And what that means is I can find the cardinality of this set. And if you are dealing with finite fields, say of characteristic P, there is actually an interesting number theoretic restriction, because 1 plus t squared might be 0 for some finite field. In some finite field, 1 plus t squared is never 0, so it behaves pretty much the same as the rational numbers. But in some other fields, 1 plus t squared might be 0, and that means we have to be more careful in the analysis. Okay, so depending on the characteristic, the size of these rotation groups, the size of the unit circle groups, they vary. Now, just to conclude today's video, we will just define now more carefully what our integral is. Now, we can define our integral, say a linear functional I sub c. So there is this subscript c on space of polynomials whole to f is called a circular integral functional with respect to S1c. Okay, if this linear functional I sub c satisfies the three conditions we talked about before, the normalization, locality, and invariance conditions. And one of the main theorems I prove in my PhD thesis is that, well, there is one and only one circular integral functional I sub c with respect to the unit circle S1 with color C. Okay, so we will have a look at three geometries, and what this theorem is saying is in each geometry there is only one and only one integral. Okay. So there are some natural questions that we can ask. For example, okay, so this is a uniqueness theorem, right? Okay, what does it look like? For example, we can establish that it exists and it is unique, but what does it look like? Can we find an explicit formula, okay, that you can use? So if I have a polynomial p, for example, alpha square plus beta square minus 5 or whatever, can I compute the integral easily? How do you prove its uniqueness? How can we be sure that there is no other integral that satisfies these three conditions that we don't maybe know of? And of course, with this field being finite or of characteristic P, for example, bigger than 2, or of characteristic 0, is there some difference? What is different in that case? So that is something that we can actually talk about in the next video or two. And yeah, hopefully you'll follow along as we talk about this the beautiful theory of integration in a more algebraic way. Thank you for watching, and I'll see you in the next video.